Mm, Hello everyone. So in this video, we will basically discuss how do we deal with database failures, right? So if we have, let's say, let's say we don't have a lot of users, right? And your database fails. So it's pretty cool. You can most modern databases have the inbuilt features where they can kind of get the original data back. That is by replaying the WAL, the write ahead log that we discussed about in the last video. But here we will discuss about what happens in distributed systems when your database fails mid write. Yeah, right. So that can cause a lot of problems. So yeah, I have a list of topics I would want to discuss over here in this video. So yeah, okay. We can start with a small recap basically. I talked about how we have masters and replicas basically, and all the writes go to masters and all the reads go to replicas. The reason for this is usually that in real world systems, most of the systems are read heavy, right? So for example, Insta, Facebook, whatever consumer apps you basically use, most of them we read a lot, so that's why we have a lot more replicas basically, right? We talked about that. We talked about let me also, okay, so just take a minute. We have a master. Okay, I'm not quite sure why is it not. Okay, whatever. So we do have a master, right? And this master basically sends its data to different replicas, and we read from these replicas more or less. So could be replicas over here, and yeah, so that's about it. Second, I also talked about how write ahead logs work. So writing data to master basically means we will first write that data on master's hard drive in a write ahead log, so that data is not lost. Then that data is written to the RAM, and after some time that data is flushed back to the master's main DB, and that is how it is stored for long term use, right? But right after we write the data in the wall, that is basically sent to other replicas. So this is what we discussed in the last video, right? So the problem over here could be, as with all distributed systems, is that anything can fail, right? That is how we build resilient systems. We can start talking by what happens. Let me just erase this because this looks extremely ugly. We could talk about what happens when, let's call these replicas now. What would happen if a replica fails, right? We could have multiple replicas, of course, and any of these replicas can fail, right? So a user usually would only query. So a user would only be querying these replicas, right? The user never sends read requests to master, like in most cases, but in some cases it can send read requests to master. We can talk about this later. So it's called maybe in read or writes or something like that. Just a second. So yeah, what would happen if, let's say, this replica fails, right? It's quite simple. The user will just then reroute its requests to this replica or to this replica, right? What if all of these replicas fail, right? The user can then just temporarily send its read requests to the master. So replicas failing is not really a big critical issue. Okay, so this replica fails. When this replica comes back alive, we could just so in that meantime the master would have had a lot of writes, right? We could just replay the wall of master again, and we could just reconstruct whatever data we have lost. The user can then continue reading from this replica. Pretty standard basic stuff, right? It's not a big problem when followers fail basically. Now leaders failing is kind of a trickier situation. In this case, a lot of things can go wrong, and we have to be kind of careful what will happen, right? So these are read requests. Let me also how do I, okay man, this is okay. So this is your user, right? So we could have a similar user. We, oh, we could have. Why I'm not able to? Okay, so we could have a similar user over here, and this user makes write requests to this master, right? So this is basically how most architectures work, right? This user could make a write request to master, and the simple question is what happens if master goes down, right? Then that would basically mean the system cannot really accept new write requests for a while. But the first question that we could ask is how do we know master is down, right? So in real distributed systems, you could have a lot of these nodes, right? A lot of these masters and replicas that are talking to each other. A very simple way to kind of understand if a master died or any of the node died is to actually just pinging it, is to actually just see if you are getting your pings back or not, right? So if a node is not replying to you for, let's say, 5 seconds or 10 seconds, you can assume it's dead. Okay, so let's assume that master dies. Okay, uh, now we can't really, just say that we won't accept writes, because what's the point of having all these databases if you can't even write to your entire system? So one of these replicas, 1, 2, and 3, one of them has to become master, right? One of that replica, all your writes are going to be sent to that replica basically, and all other replicas will start reading from it, right? Basically, and whatever the users would not then read from that replica. Basically what would happen is that these read requests would start going to other replicas, basically might go over here, might go over here, right? Yeah, so if master dies, we could actually make this as the master, and this would be then write requests, and all these would be read requests. That's a pretty simple kind of a thing that we can assume, right? So yeah, detection is basically when how do you detect if a master is down? You do that just from pinging it, waiting for like 5 seconds, 10 seconds, and then you have to do an election. Okay, so this is a part where you decide, okay, which replica is basically going to become master. The simplest way to do that is whatever replica has the most recent data, right? So we know that you write to a master, it streams its wall across all these replicas, and each wall has a number, right? So which tells us up to this this replica has up to this data from the master. So whatever replica has the most recent data, we can basically promote it to the master. This is how election basically happens. And client rerouting basically means that the user should send their write requests to the new master and reads to other replicas, right? Now there are a lot of problems that can happen over here. Basically, let's talk about them in depth. Okay, so we are going to talk about async data loss. So for here, I want to make a simple diagram. Let's say that this is a master. Okay, and let's copy this. A kind of something we have to understand over here is that all of this is, we are talking about single masters over here, right? But there can be multiple different architectures in which we have multiple masters. So this is replica 1, this is replica 2, and this is replica 3. Okay, now we're going to discuss about what happens when these fail, right? So let's assume that this is okay. I'm trying to actually make a time axis over here. Yeah, cool. So this is time axis. Okay, let's also write it over here as well. So this is time. So this is time. Okay, let's assume that there is a user over here. Let's say, let's make the user green. Yeah. So what would happen is that what would happen in a normal case scenario is that user makes a write request to the master, right? The master will process it for say like 200 milliseconds or something. So after 200 milliseconds, let's say it's somewhere over here, this master has written that data to its wall, right? This master then sends an acknowledgement back to the user, hey, that your data is kind of safe now, we have written it, right? But you must realize that none of these replicas have this data yet, right? Because no one has it. The master has not sent that data back to other replicas. Now let's assume that after 200 milliseconds, let's say after 10 milliseconds, that master streams that data across other replicas. So it sends it to replica 1, then it sends it to replica 2 and to replica 3. Now this now you can see that all replicas are getting that wall at different timings, right? Now let's say replica 1, after let's say 200 milliseconds, replica 2 has written that data down to its basically memory. So this sends an acknowledgement to the master that hey, I have that data, right? Same with replica 2, let's say after some time it sends that acknowledgement back to master, and replica 3 sends an acknowledgement back to master as well, that hey, I have my data, right? Now the question that I'm trying to come towards is, what would happen if your master fails at, let's say, this timestamp? Let's color it in red. What happens if your master fails over here? In this case, it's quite simple actually. At this time frame, all of the replicas have received that data, right? Even if master fails and no one has yet responded back to the master, they will at some point in time have that data, right? The replicas would have replayed that data and they would have it. So it's not a problem at all. Let's say replica 1 has that data already. Replica 1 is going to kind of acknowledge that data is at this timestamp, and let's say replica 1 becomes the master, it would have the data, right? But it gets a little trickier if master actually fails at this time. So if master fails at a time after it has acknowledged to the user, but before it has sent that data down to replicas, in this case we can do nothing, but that data is actually lost forever, as no replica has that data. And so yeah, this is a flaw in async replication. This is a thing that you have to deal with. Your data can be lost in asynchronous systems, even if you have multiple masters, even if you have a single master, because of this small timestamp difference. Because nothing is instantaneous, right? It's not that in 1 second everything happens. So these are real-time systems, and this is you can lose your data basically. In this case, nothing is done. Your whatever replica, let's say replica 2 has the most recent wall, that is promoted to another master, and it can just continue getting writes, right? So this is what happens in async data loss. Split brain is another very interesting thing. So what happens, let's say master 1 is down, you made replica 2 to be your new master. What happens at this timestamp when the original master comes back online, right? It might say that, hey, I'm the master, I'm still the master, why don't you give me all your rights, right? And replica 2 says that, hey, I'm the master, right? So in this system that is designed to be a single master system, you have two masters, and it can cause a lot of problems. So this whole situation is called a split brain, and to combat that, we use something called as an epoch or a term. So in Kafka, we have something called as an epoch. So what happens is that whenever an election happens, the new master is going to get a number, right? The system is going to generate a number and it's going to assign that number to the new master, and this number, whichever master or future masters would have the higher number, there would your rights go, basically. I'm sorry if let me make that clear. So let's say this master had an let's say that this master had an, and let's make it white, this master had an epoch 1, right? When the system started, it made this it gave a number 1 to this master. When we made this replica, this would have an epoch 2. Now whenever this master 1 comes back online, all the write requests must say that, hey, that whenever you write to this DB, you must have at least an epoch 2. So this master already has an epoch 1, this master would straight away discard that write, because this is not quite literally the most recent master. So this is how Kafka and Zookeeper work. They assign epochs to their basically replica to their new masters. And yeah, the last problem is timeout timing. Timeout timing. Yeah. So as I told you, how do we detect if a node is dead? That's basically through pinging it, right? Let's say we set the timing as kind of arbitrary. Let's say we say it's 10 seconds, right? So if master has not responded to us for 10 seconds, we say that master is dead. But it could also be the case that there's a lot of data that we wrote to the master DB and it's just processing it, right? What if at the 15th second the master was not really dead, but it was just processing that data, and at the 15th second it would have given the acknowledgement back to the user and would have sent that data over to all other replicas, right? In that case, master was not actually dead, but we just assumed it to be dead, right? Or so this would mean that we can increase our timing, right? And not make it 10 seconds, but let's say we could make it 15 or 20 seconds. But this would mean that, okay, if the master actually died, we would have to pause the entire system for 20 seconds, right? This would be worse because your system's down. What would you do in this case? The opposite of it is, okay, let's actually make it quite less. Let's make it 2 seconds, right? So we would wait for the master for 2 seconds. If it has not responded yet, we could just say that it's dead. But again, what if it's just processing data and you kind of you're just assuming it to be dead, but it's not. So these are all scenarios, all drawbacks that you have to kind of think about. Usually in modern day systems, it's actually around 3 to 4 seconds. That's what's done in Postgres and all. So yeah, timeout timing is a problem that can never go away. There's always uncertainty, but you just have to pick one and kind of stick with it. So yeah, this is about what happens when a single master fails, right? Yeah, and that's all about for this video. But in future, we are going to discuss about what if we have multiple masters. And in another future video, what we are going to talk about leaderless applications, basically, in which there is no master. So even if some nodes fail, the system can continue accepting writes and also serving reads. So that's where we will discuss about quorums. So yeah, thank you so much for watching.